Hello again, and welcome to the third of three lectures for General Physics 2 in this suite dealing with the interference of light. In this one, we talk about the phenomena of diffraction. So recall that when we're talking about interference broadly, we're talking about waves from two sources, and in places, those waves will arrive in phase with one another and cause constructive interference. So if we're talking about light waves, this is a bright spot or a brighter light than either of the individual waves. But in other places, if they arrive out of phase with one another, they will destructively interfere, and in the context of light, produce no light, a dark spot. So what do we mean by diffraction? Well, diffraction is a broad name used for talking about the bending of waves around some sort of obstacle. And very often it is talked about in the context of waves traveling through an opening in something and then bending as they go around the edges of that opening. Well, Huygens, I believe Dutch, was the first to talk about this phenomena and give us a model for thinking about the phenomena of diffraction. So Huygens' principle says that every point on a wave front, so a wave front is just a line that that was all formed at one point by the wave source. If you played around with the wave simulator in the interference of light lab, it shows you those lines moving across the screen. So if we take every point on a wave front and think of it as acting like a source of tiny wavelets that move forward with the same speed as the wave front at a later instance is the surface that is tangent to the wavelets. There's a lot tied up in there, but basically it's saying whenever you see a line that is a wave front, you could just treat that line as a whole series of dots, and you could draw the waves that go out from a point source, right? These just circles from that dot. But then where all the circles overlapped, you can trace your way around that, and that will form your next wavefront. Well, you can do that with plane waves, and it'll just result in the plane wave was here, and now the plane wave's here, and now the plane wave's here. But it's particularly useful when you think about these plane waves moving through an opening. So here was my plane wave, and then it got into this opening, and I treat this as a whole bunch of little point sources, 5 in this particular artist's depiction. Well, if I then trace a circle around each of those 5, that forms the basis for my new wavefront in the next instant. And so then if you trace around the edges of all those circles, you get a shape sort of that is shown here. And so you can see that even though in the center the wave is going to keep going in a straight line, out on the edges the direction of the wave has changed, and now it's bending and moving outwards along those edges. Well, the amount of diffraction is an interesting thing to think about. So here's a little thought experiment. If you are anywhere where there's a door opening, right, and you get around the corner so you're sort of hidden from view, if somebody is coming towards that door and calls for you, producing a sound wave, you will have no issue in actually hearing that sound around the corner. But you won't see them directly, right, until they get through the door opening. So this tells us that, light and sound waves behave differently through these openings. Why is that? You can hear sound around most corners, but you can't see light around most corners. What's different? Well, what's different is sound and light have a lot of differences, but one of the chief differences is they have very different wavelengths in terms of their waves. Sound waves are much larger wavelengths than light waves are. So this is a ripple tank picture again. So these are water waves that it's showing us some diffraction effects with. But the same wave principle applies across many categories of waves. So here in this ripple tank, making a whole bunch of straight wave fronts that are moving through the ripple tank. And here in picture 1, I don't see very much diffraction out at the edges. And one thing to note is that this opening is pretty darn wide. But when you look at opening number 2 with a much narrower opening, the amount of diffraction is much more evident here, the amount of bending and spreading of the light outwards. And what's different is obviously the narrow width versus the long width. So the extent to which the wave bends and the extent to which we observe a lot of diffraction actually depends on the ratio of the wavelength to the width of the opening. And the bigger that ratio is, the more diffraction we will observe. So if you have significant diffraction, it's a situation where the wavelength of that particular kind of wave is larger compared to the width of the opening than other kinds of waves that are not being diffracted. So what does that mean in the context of light experiments? Well, you may have noticed when you played around with the simulator for the interference of light lab that if you do a single slit, you actually still get a pattern of light, dark, light, dark, light, dark on the screen, but it looks different than the pattern for a double slit. So if there were no diffraction, light that's shown through a single slit would just form a narrow beam of light. But what actually happens is if we shine light through a narrow slit, we see a pattern on the screen where there's a pretty broad, bright spot in the center of that pattern, but then off to the side there are smaller, dimmer, but still bright spots with some dark spots interspersed in there, forming a pattern. And we get an interference pattern through a single slit, just like we do get an interference pattern through the double slit. In my experience, the single slit's a little bit harder to think about and conceptualize, but it exists nonetheless. And in fact, if you do this experiment in the lab, when you do the classic Young's double slit experiment, what you observe if you step back from the system and look at it is you actually see the double slit behavior within the center bright band that it comes from the single slit behavior. So you actually see the superposition of both effects when you do this. We're going to use this Huygens idea of multiple point sources, though, to help us make sense about what's happening here. So I have my plane wave coming through my opening, but I'm going to treat it as a whole bunch of point sources. And then somewhere way far over, which the artist has not shown here, there is going to be a screen, and I'm going to see a bright spot in the middle, and then some dark spots off to the side, and then a bright spot next to it, etc. And it turns out when you were working out mathematical models for single slit diffraction, it's actually easiest to think about where those dark spots are. So that midpoint, that center bright fringe was here where all of the light from all of those individual point sources travels basically the same distance to get there. But somewhere off to the side is going to be this place where we have our first dark fringe. What's happening there? Well, again, if I think of this as being 5 points of light, you can do any number in this space, but you just need some number of points of light in there. That first dark fringe is formed at a certain angle where the distance across the opening of the slits is a whole number of wavelengths. Why is that? Well, if we look at this artist image here, right? Light that comes from point 1 goes up at some angle. Light that comes from point 3 goes at about the same angle, but that light has to travel a half a wavelength different distance than the light that came through point 1. And that means 1 and 3 are going to cancel each other out. If we did 2 and 4, we would find the same thing. Light from number 4 is going to travel a half wavelength further than light from number 2 and cancel out. And you might say, well, what about number 5? Wouldn't number 5 be left? Yes, in truth, that would be the case. But we're only showing 5 points here. What if we filled this space in with 5 million points, right? And then, 1 cancels with whatever the 1 is in the million, 2,500,000 that's in the middle there. And then 2 cancels with the 1 just below that, and 3 cancels with the 1 just below that, and 4, etc., right? 99.999% of the light is going to get canceled out by treating these all as individual point sources, leaving only the one that's at the very bottom. So I get my first dark spot when that is 1 wavelength of extra distance down at the bottom. I get my second dark spot when that distance is 2 wavelengths down at the bottom. For the same reason, now you can think of 1 is canceling 2 and 3 is canceling 4, and you could fill in the gaps all the way down that as well. You can keep this same pattern going, right? You can go to a place where now there's 3 wavelengths of path difference across the opening of the slit and find the place of a third dark fringe. So in general, the sine of the angle that the light is going to at that distant screen has to be some whole number of wavelengths divided by the width of the opening that you're talking about. In contrast to double slit experiments, when you do this single slit, again, you don't see these sort of evenly spaced interference patterns. You see a bright spot in the center that's really bright and really broad, and then your dark spot off to the side, and then a narrower and less intense bright spot, usually to the side of that, and then another dark spot, and then an even dimmer bright spot off to the side, and then usually, it depends on the situation, you get 3 or 4 of these, and then it sort of fades out to where you can't see it any longer. But intensity-wise, the huge bulk of the intensity is still in that center bright spot, and much less intensity off to the sides of the pattern. So that's single slit diffraction, but you also have diffraction gratings, which is a broad term used for light that passes through a whole series of slits in a material. Now, if you've ever put on one of these pairs of glasses, I happen to have one sitting on the desk here, at some sort of science show or whatever, you've actually experienced a diffraction grating, because looking through these, you see the effects of light passing through a whole bunch of narrow slits. But you can't actually really see those narrow slits on there. It's pretty much just looks like a transparent piece of plastic to the observer, but there's a whole bunch of little slits that are etched in there actually optically. And you get this interesting effect when light passes through there. If you pass light of a single color through a diffraction grating, you get the same interference pattern actually that you get through a double slit experiment. And in fact, the math is exactly the same as that for a double slit experiment when you're dealing with a diffraction grating. But if you pass it through white light, right, like I'm looking through colored light here, you end up seeing these rainbows because the amount that light is diffracted depends on the wavelength of the light. Different colors of light have different wavelengths, and so I get constructive interference of different colors at different distances along the screen. So looking at something through a diffraction grating or even a reflection off a CD gives you a variety of colors rather than bright, dark, bright, dark. So this diffraction grating, again, is a whole bunch of closely spaced slits. And so here's an artist's depiction from a textbook about this, right? I have a whole bunch of different openings, and light is traveling to a place in the center where it's bright, but then you get other bright spots off to the side, and you can again characterize them with some angle relative to the middle to figure out where those locations of the bright spots are. So again, I said the geometry here is very similar to a double slit. And in fact, here we're just going to deduce it by thinking about 2 of the slits. And so 2 of the slits at some angle, the path length difference needs to be some whole number of wavelengths to find our constructive interference spots. So 1 wavelength, 2 wavelengths, and obviously all these angles are being greatly exaggerated by the artist. But you can do the same math that we did back in the double slit, that the sine of that angle is equal to some whole number of wavelengths divided by the distance between 2 of these openings on the diffraction grating. And you can do the same thing about dark spots if you care to do so. What's different when you use a diffraction grating, and you may have noticed it in the picture on the previous slide, is that in a double slit, right, we get bright, fading off into dark, fading off into bright, and then ramping up into bright, fading off into dark, etc. In a diffraction grating, you get the brightest spots to be much narrower than they are in a double slit experiment. And then in between, you get really faint lines in between as well, where there are constructive interference happening from portions of the pattern, but not from all of the openings in that pattern. So you can always tell a diffraction grating interference pattern is different than a double slit simply because of the narrowness of the lines that you see here in the bright spots, as well as the fainter bright spots that occur in between. Where does all this diffraction stuff actually happen? Well, the most useful, in my opinion, thing of diffraction has been in experiments that reveal to us the nature of matter. So you may have in a chemistry class studied the fact that many materials occur in these crystalline forms, right, where there's a regular pattern of atoms that form this particular molecule. How the heck do we know what that pattern is, right? Because we don't have microscopes that can see on that level. We need to be able to deduce what the patterns are of these crystals. And one of the ways that scientists do that is through X-ray diffraction. So these regularly spaced atoms actually act as diffraction gratings, because if you shoot X-rays at a crystal, when they hit an atom and bounce off, that's the same geometry as light passing through a whole series of openings in a diffraction grating. You're just looking at the reflected beams, if you will, rather than the ones that are transmitted through an opening. So again, you can't do this with visible light with material because the visible light wavelengths are too long. So you have to have something that has a shorter wavelength in order to actually accomplish this. And X-rays are commonly used in this particular imaging technique. And you can then, observe this diffraction pattern. So these are the quote-unquote constructive interference spots that we see show up on a piece of film, where we see these bright spots. And from that, you can work backwards through the geometry to figure out, hey, this is how my crystal is arranged that I did this diffraction of. This was also very instrumental in Watson and Crick developing their model of DNA. It was a graduate student of Rosalind Franklin, I believe, who actually used this X-ray diffraction and took a relatively famous image that's shown here of the structure of DNA, and that fed into Watson and Crick's model of how DNA was structured. So diffraction, again, broadly, the bending of any sort of waves, but diffraction often in science is used to talk about the imaging of things that are on a smaller scale that cannot be observed directly optically.